Okay, I'm Dylon. Today I'll talk about lattice-based cryptography, and in particular, the ring LWE. So I'll begin with some motivation. That's why we choose use ring LWE instead of the standard LWE. In standard LWE, we have a public matrix A and a secret vector S. And we do a multiplication, inject some noise to get a pseudo-random result. Note that we have this A is represented by like n squared elements, S is represented by On elements. So here we have we start from n squared elements and end up with the elements. This is also end up with elements for n. So actually we waste too much bits where we start, and this is where the efficiency comes from. Well, in ring LWE, we have an element which is A is a public ring element in RQ, and S also an element in ring RQ. And we multiply them together and inject some noise to get a result also in RQ. And this A can be think of as represented by n elements, as also n elements. So we start from n elements and end up with n elements. This is more efficient. And to relate ring LWE to standard LWE, you can think of this multiplication can be represented as, so let's say A is represented by A1 to the AN, which is the coefficient of the polynomial ring, and S is also represented as S1 to the Sn. And this polynomial multiplication can be written as a matrix vector matrix vector multiplication. This vector is S1 to the Sn, and this matrix is something like A1 to the AN in the first column, and the second column is some permutation of the first column. Let's say it's well, recall that in a standard LWE we have a fully random matrix where each element is independent and random values. Here, this matrix has some internal structure in it. Actually, there is only n bit randomness, and we use n bit randomness to generate the whole matrix. And one problem is that if this matrix is not fully random and it has some structure, it may lead to some attacks. So we need to carefully instantiate this ring. And a popular choice is by instantiate by a polynomial and a quotient ring where the quotient polynomial is x2 n plus 1, where n is the power of 2. So in the following, I will give some supporting evidence that why we consider this to be secure, or why it has to be this form for it to be secure. So first, I want to claim that in its general form, this X must be irreducible. Why is that? Because you can take some analog in the number theoretic constructions, like like in RSA, you want to work with modular n, which is a product of two prime numbers, And if this n is can be decomposed by a very a small can be factorization into small primes, then this will lead to many attacks. So I will not show you an attack on the case where you choose P to be a polynomial that is not irreducible, but you can basically get some inspiration from this. PS has to be reducible to defend some certain types of attacks. So I'll just claim this. And secondly, I want to say that x to the n plus 1 is irreducible if and only if n is a power of 2. There is no way to choose n, no other way to choose n to make it irreducible. Why? And I prove by contradiction. Assume that there exists odd number divides n, and we can write n as p times n prime, where p is an odd number. I'll directly show you a factorization of this polynomial. It can be factorized as in order to prove this, rearranging this equation is sufficient to prove this term I'll denote here by s is equal to this term divided by this term, right? And let's first compute this as. So it is actually a geometric series with q equal to minus x. Right? And from the sum formula of geometric series, its sum is and there are p terms in total, and we plug this into this formula, will give us so this completes the proof. So, as I just proved, there's no other way to choose n. And then I'll show that if n is, okay, should be this direction. Now I prove that if n is choose to be a power of 2, then this polynomial is indeed irreducible. I should be more precise, it's irreducible over z, or over rational numbers. In order to prove this, let's start with okay. This is true, right? So firstly, this is true. And secondly, so here k is the odd number. So we split this into odd number and even number. This is also true, right? And you observe that this is equal to this. And by changing a variable, this term is also equal to this term. So we must have this term is equal to this term. And all of roots, since k is a whole number, and this is power of 2, so all of its roots is a complex number, not in the integer. So which completes proof. Okay, that's all. Thank you.